Good evening, everyone, and welcome to the stream. Tonight we are going to be solving Day 24's puzzles for Advent of Code, the penultimate puzzles of this year. As always, I'm going to be working in C++, and all of the code that we write tonight will go up on my GitHub repository. That's github.com/craig-chasseur/AOC2020. You can see that on the screen right now. The links will be down in the description. If you're watching this on Twitch, you can always catch stream replays later on my YouTube channel at youtube.com/spoonboy42. If you're watching on YouTube, the live streams happen nightly on Twitch at about 9 p.m. Pacific time. So, yeah, we have about 5 minutes until tonight's puzzles unlock. It'll be interesting to see, these last couple of days, how difficult the puzzles are, or if we get some real thinkers, if they stump us or not. We'll see. We'll find out soon, I guess. Last night's puzzle was pretty interesting. We played this cups game with the crab on our raft, and we got up to a really huge number of cups, 1 million cups, and 10 million rounds of the game. And, at first I had put together a brute force solution, and it obviously wasn't going to finish in time, but we managed to find ways to kind of tweak and improve on that brute force solution and make it so that we still had to simulate all million moves of the game, but each move could be simulated very quickly because with the aid of this lookup table where we knew the position of all the different numbered cups exactly. So yeah, had fun last night. Looking forward to seeing what we do tonight. As always, if you have any questions, feel free to drop those in the chat. If you have questions later on watching this stream on YouTube, feel free to leave a comment, and no matter where you ask the question, I'll do my best to answer it. So I'm looking at our calendar here. After our very circuitous route, we are getting closer and closer to our island vacation, sailing on the raft with our crab buddy. Hoping to take a well-deserved break at the end of this. So in the few minutes left before tonight's puzzle unlocks, I'll go ahead and do what we do every night and just set up the basic scaffolding for tonight's puzzle solutions. So we'll make a directory for day 24. We'll make a source file for part 1. We'll have just this very minimal C++ program in here, just return 0, and we will write the build file so that the Bazel build system that we're using knows how to build it. Go ahead and make sure that that compiles and runs fine. And it does. And as we've been doing the last several nights, just to get a little head start, we'll go ahead and add the check library and the IO library that I have in my repository here that just includes some pre-written functions for assertions and for doing file I/O, because most days we wind up needing those. Just add the dependencies for those in the build file as well. Build and run again, and we're good to go. Just about a minute and 15 seconds until we get tonight's puzzle. I wonder if we'll actually make landfall on the island tonight. You can see more and more of the picture is filled in, all the places we've been, the sea monster we discovered. That is a really fun thing about Advent of Code, is having the story unlock and also the illustration of our journey as we go. Obviously, it takes a lot of work to craft these puzzles. So shout out to Eric Weistel who does this. But it also takes a lot of creativity to write the story and have the illustration and everything, and I appreciate that. It's a lot of fun for all of us to go through this, and I appreciate that somebody took the effort to give that to all of us. It's kind of an annual holiday gift. All right, day 24. We made it to the island. All right. Thank you, Crab. Here in the lobby, you discover problem. Floor's being renovated. Can't even reach the check-in desk until they finished installing the new tile floor. They're hexagonal. Interesting. Tiles are all white on one side and black on the other. Start with the white side facing up. Lobby is large enough to fit whatever pattern might need to appear there. Got a list of tiles that need to be flipped over. Each line in the list identifies a single tile that needs to be flipped by giving a series of steps starting from a reference tile at the very center of the room. Every line starts from the same reference tile. As the tiles are hexes, every tile has 6 neighbors. Oh my. Okay. For example, alright, no delimiters. Each time a tile is identified, it flips from white to black or from black to white. Tiles might be flipped more than once. The example above. Oh boy. 10 tiles are flipped once to black. 5 more flipped twice to black and then to white. So 10 tiles are black. Okay. And let's get our puzzle input here. So I think, we can go ahead and read that input and just see how big it is, but probably pretty big, as these puzzles tend to be. Yeah. Fair number of instructions there. So I think the real key here is to come up with a coordinate representation for hex tiles. And then we can use that to, and then we can, write the functions that will navigate through those hex tiles according to those directions that were given. But I'm seeing that the directions, you can go straight east or straight west. So we imagine that, like that east to west line is a straight line. Then there's southeast, southwest, and northeast and northwest. So we can have a coordinate system here, but we have to remember that, like, even in odd lines are, displaced by each other, are displaced, so that they go over one. But I think this is definitely still doable here. So I wonder if we actually want to make a grid, or can just do a sparse representation of tiles. But yeah, so let's write let's write a little class called hex coords, and this class will know, depending on whether it's we'll have an x, we'll have essentially an x and y coordinate in this, but we'll be able to handle those offsets into the subsequent rows. So this will be our starting point for navigating the hex grid. So we can have an x and a y part of that. Defaults to the origin, which we'll call which will be the center. So so to go east from given hex chords, we just return the same hex chords, but x is going to be, let's say, we'll say the east direction is positive and the west direction is negative. Is that initialization going? Okay. We'll just go ahead and copy it and then modify x. West is similarly going to be pretty easy, but then when we go to the adjacent rows is when this gets a little tricky. Now that should be that should be we reduce x, don't do anything to y. So I'm going to sketch a little something, and maybe I can show it to you in the camera once I do sketch it. But what I'm going to try and do here is just lay out some hexagons and make sure that I get the the x values for the adjacent rows right. And I will show you my sketch once I've done it here. I mean, I suppose we could just define a coordinate system that has, infinite shifts one way or the other, but you know what? Not the worst idea necessarily, because, as long as these all... You know what? I'm actually kind of tempted to do that now. Oh, we'll see. You know what? We can define, x0 as being kind of like a diagonal line through the space. And so in our hex space, x and y are not, strictly perpendicular to each other, but I think we can still make this work. So, let's see here. So going south, we are going to decrement y, but we will say that the line for x equals 0 goes from northwest to southeast. So we will leave x the same in this case. Now southwest, x should be reduced by 1. So obviously y goes up by 1, and if we're going northeast, then x goes up by 1 as well. And then finally, northwest will be on that northwest to southeast line where x stays the same, but we do need to increase the y. Okay, so there are our navigation functions. The other thing that we're going to want for this hex chords class is to make it so that we can do equality and hashing for it, because we're going to maintain some sets of coordinate of hexes that we've reached to keep track of what's on the black side and what's on the white side. So we'll write the equality operator. And then we will make this compatible with the absol hash framework. You've seen me do this a few times before, but basically you write this inline friend function, absol hash value. It shouldn't be inline vector. It's just it included that for us, but I'll show you how you can do this here. And then no, it's just absol hash value. It doesn't need that prefix absol. But then we use h combine. Move this h just represents the state of the hashing computation, and then we put in the things that we want to be hashed in. So that's just the x and y inside these hex chords. Oh, that should be move, that's why. Now we've done something here that is... Oh, yeah, I need that open paren, that's why. There we go. So now this type can be used in hash-based containers. So now let's just write a little function that or we can make this a method of hex chords, but we'll just say call this apply path. And we will take the path, specified as that sequence of directions like we have here. And so you start with this current one. Take off that first character, and this could be north, south, east, or north, south, east, or west. If it's just east or west, we do it directly. If it's north or south, we need to take an additional character. Make sure that the path isn't empty, but we should take the next character to see what we should do next. And if it's neither of these characters, then it's not a valid path, and we'll just check fail in that case. And we're going to want to do something very similar for south here. So I'll copy and paste and just change a few things. Okay. And then, again, we'll have a default case in the outer loop here with check fail, because we shouldn't see anything else. So we keep on, changing the current position as we go through this path, and then we will finally return it when there's no more path to follow. Okay. So in the outer part, the overall structure of the program here, we are going to read in our list of paths. So first we're going to check that argc equals 2. That we expect 2 arguments, the program name itself and the input file that we're reading. Whatever. We'll use our read lines from file routine to read that in. So let's see. all tiles start with the white side facing up. So we will have a flat hash set of the black tiles. Need to make sure to include the header for that. You also need utility for move. Okay. So for each of those lines, we will start with hex coordinates at the origin, 0, 0, and apply the path, and then we will get our destination tile. And then we will try and place it in the black tiles, but if we find that it's already in the black tiles, then we're going to erase it, because it would flip back to white. So we'll say try in place tile. Or just in place tile, I guess. Yeah. There we go. So if not inserted, that means there was already an entry in black tiles for that tile, and that iterator that we got as the first part of that pair refers to it. So we'll just say .erase iter. And then we just print the size of the black tiles set, and that will be the number of tiles that are painted black, or have the black side up. Okay, so we used flat hash set and string view here. Let's add those to our dependencies. Flat hash set and the strings library. So let me take the test input from the website here of the paths. We will use that to just as a check on our program here. But let's run that first on the test input. That gives us 10, which is correct. Let's run that on our actual puzzle input. 521 black tiles. Let's see if we are correct. 521. All right, on to part 2. The tile floor in the lobby is meant to be a living art exhibit. Every day the tiles are all flipped according to the following rules. Okay, this is like hexagonal life now. Any black tile with 0 or more than 2 adjacent is flipped to white. Any white tile with exactly 2 black tiles immediately adjacent to it is flipped to black. Here, tiles immediately adjacent means the 6 tiles directly touching the tile in question. The rules are applied simultaneously to every tile. Okay. How many tiles? Okay. So let's go ahead and copy our part 1 solution to part 2, and let's implement this cellular automata with the living art exhibit in the resort. Oop. Need a destination, of course. Okay. So, one thing that let's see. Any white tile with exactly 2 black tiles immediately adjacent to it is flipped to black. So we can still look at just the set of black tiles and those that are immediately adjacent to black tiles, because no white tile that is not adjacent to at least one black tile, and specifically it has to be exactly 2, is going to be flipped to black. So yeah. We'll make a new class to represent the state of the overall floor. And internally, we're going to have a flat hash set of hex chords to represent those black tiles. And for the constructor here, we will pass that list of all the lines, and we will use it to initialize the set of black tiles. So we're basically doing this same loop here now in the constructor for floor. The other thing that we will do here is for hex chords, we will add a method that returns all of the adjacent coordinates. And we will just do that as the set of east, west, southeast, southwest, northeast, northwest. You're noticing that this is going to become something very similar to our 4-dimensional game of life that we played on a previous day's puzzles. I want to say that was day 17, if I'm not mistaken. Yes, day 17, where we also coded up a cellular automata. So, fun times all around. And then we'll have this step function, which just advances the state of the floor to the next day. So what we need to do is we'll start with a flat hash set. We'll have candidate tiles, and it will start with all the black tiles that we need to inspect, and then all the tiles that are adjacent to black tiles, which could also include some white tiles. yeah, we can just insert the range here. Okay, so these candidate tiles are all the things that might be black in the next iteration. So that includes all of the currently black tiles as well as all the white tiles that are adjacent to a black tile. So we'll have this helper method, black in next iteration, that will tell us whether a given hex will be black in the next iteration. So we'll also have another helper function here that will just count the adjacent cells for a given set of coordinates. So So we'll add 1 to adjacent black for each of the adjacent hexes that is present in black tiles. So if this cell is black already, if it has 0 or more than 2 black tiles immediately adjacent to it, it is flipped to white. So we'll just adjacent black there. So if it's 0 or more than 2, return false because it will be white in the next iteration. Otherwise, the cell stays black. For a white tile, if it has exactly 2 adjacent, it is flipped to black. So here we just return adjacent black equals 2. Okay, so we've built up our set of candidate tiles. We'll now have a set of the tiles that are black in the next iteration. And then for each of those candidate tiles, if it's black in the next iteration, we put it in that set. And then finally, we replace the set of black tiles with the next version. So now all that our main program needs to do is create this floor and run it for 100 steps, and then we'll print out the number of black tiles. Okay. Let's make a build target for this and see if it works. I think we should have all the same dependencies as part 1. Let's do it on our test input first to see if we get the correct answer there. 2208, that is correct. Let's do it on our actual puzzle input. 4242. Ooh, a very lucky number. I like that. Let's see if that's correct. All right. An 851 on the leaderboard. Not bad. Okay. Wow, we have solved the penultimate day's puzzles. There is just one more day of puzzles to go with Advent of Code. Thank you so much, everybody who has been watching these streams, who have been following along as we solve the puzzles. As always, the code for the solutions that we've written is going to go up in my GitHub repository. That's github.com/craig-chasseur/AOC2020. You can always find the stream replays on my YouTube channel. That's youtube.com/spoonboy42. No matter where you're viewing this, you can find all the relevant links down in the description. Today's puzzle was pretty fun. It was, once again, a cellular automata game. I think part 2, especially, it's just so similar to what we did for day 17, which was also a cellular automata game. Like, the specific rules are different, and the fact that, we're using a hex-based grid is different, for our coordinates is different, but it is really similar to what we did with that 3D and then 4D Game of Life. So, algorithmically, aside from the little details that apply the rules for, like, whether a tile is black in the next iteration, and of course the different coordinate system, but having this set of candidate tiles and then evaluating all of them, moving on to the next, storing them in this sparse representation like this, it is so similar to what we did for day 17. So I think that we had a good solution there, and then we could easily reapply that knowledge to tonight's puzzle. So once again, thank you for watching. I look forward to seeing you all one more time as we solve the final puzzles and actually enjoy our island vacation here on Advent of Code. I can almost smell the daiquiris. I'll see you all again tomorrow night. Good night, everybody.